Hello, everyone. I'm Xingyuan Yu from Shandong University, and I'm going to give a talk about the work entitled Feistel-like structures, revisited classification, and cryptanalysis. This is a joint work of Bing-Sun Zejunxiang et al. From National University of Defense Technology and Hubei University. Unfortunately, the authors couldn't be here today, so I'm here to on behalf of them to give a talk. How to use it? Maybe I should.
Yeah, people have had trouble with this all day, so should.
It doesn't work.
Okay.
Oh. Okay. In this paper, the authors revisited the unified structures for Feistel-like structure, and they proposed some new definitions like affine equivalence and self-equivalent structures, and refined field division round. With these definitions, they show some equivalence between different structures and give some guidelines for the design and analysis for stylus structures. When we constructing a new block cipher, usually we first decide on the iteration structures, SPN structure of Feistel-like structure. Feistel-like structure include Feistel structure, line-mercy structure, and source-heavy generalized structure like SM4 structure, and target-heavy generalized Feistel structure like Mars. Recently, Liu et al. Proposed the unified structure for Feistel-like structures. They characterize the Feistel structure like this. Deep branch generalized Feistel structures first passes through the matrix AI for each branch, and then the round function f, and then multiplied with the matrix B. And they show the conditions and that unified structure is immutable if the following equations hold. And pi is a branch permutation. First of all, we proposed some questions before we show our contributions. We note that there are some links among different structures. If permutation pi are different, some cryptologic properties remain the same for some Feistel-like structures. And SM4 and mass structures cover the same number of rounds for the longest impossible differentials and the longest zero correlation London house. The generic results of the meeting in the middle attacks against both source-heavy GFS and target-heavy GFS are the same. So we wonder if there are any equivalence for the universal cases between different structures, like source-heavy structures or target-heavy structures. And the second, there are some links of impossible differentials, zero correlation, Lana house, and integral distinguishers. So the question two is, for what kind of structures are the impossible differentials equivalent to the zero correlation Lana house? And for generalized Feistel structures, although some structures can achieve field diffusion, there is a probability one differential which covers any round. So question three is it possible to redefine the field diffusion round such that the probability security evaluations of the unified structures against impossible differentials and their correlation house can also be covered. Here we show a description for the unified structures. A GFS which has D branches, each branch is n bit. The state first multiplied with the matrix A, which maps the finite field ND to the finite field T. And then the rounded function f, which is a mapping over the finite field T. And then multiplies with the transpose of BT, which is also a mapping from the finite field ND to the finite field T. And BT is the set of all the mappings over the finite field T. And pi is a branch permutation, which after the XOR with the state X. And one round encryption FAB pi is a mapping from over the finite field ND. And the unified structures is defined as all the encryptions which the run functions in the site BT. And an R-round iteration of the unified structures is shown like this. Each round function is not the same because the round key is independent. And we show an instance for SM4-like structure and a mass-like structure. For a four branch SM4 structure, the matrix AS equals OIII, where O equals zero matrix and I equals identity matrix, and BS equals IOOO. There is just one target. It's a source heavy GFS. And mass structure is whose matrix AM equals IOOO and BM equals OIII. The permutation pi is a blockwise cyclic shift operations. Then we define the dose structure. The dose structure of a unified structure is defined as for the unified structure, AB pi is defined as the unified structure BA pi, swiping the position of A and B. And we can check that the dose structure of SM4 structure is mass structure and vice versa. And here we use A with superscript R to denote the matrices like this. We'll use it later. For unified structure, the following conclusions holds. The unified structure is immutable if and only if the matrix, the product of A and the transpose B equals 0. And there exists an integer R, then the rank of AR equals the rank of BR equals ND. Otherwise, there always exists a differential characteristic with probability 1 for an arbitrary number of rounds. Alpha to beta is an R-round impossible differential of the unified structure if and only if alpha to beta is an R-round zero correlation line of its dual structure. And in this paper, we focus on the regular unified structure. The regular unified structure is defined as the unified structure which satisfies the following five conditions. first it is invertible, then the sizes of the round functions equals the size of the branch, and the round function are permutation, and the order of pi equals the number of branches. Finally, AR and BR are invertible matrices. Then we show the definition of the equivalence between ciphers. Let E1 and E2 be two block ciphers if there are bijective affine mappings P and Q such that for any X and K, E2 equals the components of Q, E1, and P. Then the two ciphers are defined to be affine equivalent. And then we can show how to define the affine equivalence between structures. Two unified structures are said to be affine equivalent if there exist two affine mappings P and Q that establish a one-to-one correspondence between sets of instance of epsilon 1 and epsilon 2 in following manners. For any instance E1 epsilon 1, the transformation, the components of Q, E1, and P results in an instance within E2, and conversely, it also. And we show a regular unified structure can always be a affine equivalent to a mass-like structure, which is a target-heavy structure like this. And this is called a X-type normalized form of the unified structure. We can check if two unified structures are equivalent, use the normalized form with the matrices A and B and this equation. Famous. And we show that SM4 structures are equivalent to mass structures. And we can show that unified structures can always be affine equivalent to source heavy GFS, which is shown like this. So every source heavy GFS corresponds to an affine equivalent to the target heavy GFS and vice versa. Then the definitions of self-equivalent structure. If an unified structure is equivalent to its dot structure, then it's called a self-equivalent structure. And we can check the equation like this with matrix A and B to show if a structure is a self-equivalent structure. We can show that both SM4 and mass are self-equivalent structure. Generally, for matrix A and B are both block matrices whose elements are either identity matrix I or zero matrix O. If every block in A XOR with B is identity, then it's a self-equivalent structure. And there are some relationship between the integral distinguisher and impossible differential and zero correlation Nannerhaus. The maximal rounds, the number of maximal rounds of the impossible differential equals that of zero correlation Nannerhaus and less or equals than the maximal rounds of integral distinguisher. And to ensure a structure can achieve field diffusion without probability one differential, we redefine the field diffusion round. The definition of refined field diffusion round is shown like this. And we can check the refined field diffusion round of structure deduced from AES2. And for regular unified structure, the refined field diffusion round is 2D minus 2. We also have a procedure to calculate the refined field diffusion round of the unified structure. And we check that the refined field diffusion rounds of Feistel SM4 and Mars structures are 2, 6, and 6 respectively, if round function are permutations. And we show the longest impossible differential of the unified structure covers exactly 2/3 of refined field diffusion round plus 2, which equals 3D minus 1. Okay, in this paper, the results could give new guidelines for both the design and crypto analysis of Feistel-like ciphers. A source-heavy GFS is always a fine equivalent to a target-heavy GFS with the same round function f and the same round key. For self-equivalent structures, there is a one-to-one correspondence between the impossible differentials and the zero correlation London-Haus. For self-equivalent structures, the longest integral covers at least rounds of longest impossible differentials, zero correlation London-Haus. And both of the longest impossible differential and zero correlation London-Haus of D branch SM4-like structure covers exactly 3D minus 1 rounds. Okay, that's all. Thank you for the attention.
I think since you're not one of the authors, you're just giving the talk, it might be better to take questions to email to the authors.
Yeah, thank you.
Thank you. Our next speaker is Lucas Stenes, talking about recovering symmetric cryptography from hardware circuits. At least you didn't step on it.
Okay, so
I think you want to point the remote at the screen that seemed to be working. I don't know for sure if that's it. Everybody's had trouble with remotes. So.
Yeah, okay. Seems to work. Okay, so thanks for the introduction and hi all. I'm Lucas and I'm presenting Hawkeye, which is the tool for recovering symmetric cryptography from hardware circuits. And Hawkeye is joint work with Gregor Leander, Christoph Paar, and Julian Speit. So, no, it's not working. Yeah, okay, that's it. Okay, so let's start with a bit of motivation. And for this, let's look at symmetric cryptography. I mean, we are in a symmetric cryptography session, so I assume you are all familiar with symmetric cryptography. We have three parties, Alice and Bob, they are communicating. And then there's Charlie, who is eavesdropping on Alice and Bob. And so Alice and Bob use symmetric cryptography to protect their communication. And metaphorically speaking, they put their message in a box, in a very solid box. And then they put a padlock on the box. And this padlock is so strong that Charlie cannot break it. And then when we actually use symmetric cryptography and not talk about the picture, we just use AES, right? Of course, it doesn't have to be AES. It could be Chacha or Ascon or something similar, right? Just a cipher that has been studied in public and where we as a community agree that it's secure. There's Kerckhoffs's law, and it makes no sense to use anything which is not deemed as secure, right? Well, of course, in the real world, there are many examples where this actually goes wrong, and people use ciphers that are actually quite insecure. And here I have one example. Of course, there are many more, but unfortunately, we don't have the time to talk about all of them. But the example I briefly want to cover is Tetra. So Tetra is a standard for terrestrial trunked radio. And yeah, it's used around the world by police forces for radio communication. And so in Tetra, there are multiple ciphers. They are called TA1 to TA4. And as it turns out, in TA1, which is the export version, there is, well, let's say an intentional weakness. So it takes 80-bit of key, and then it's compressed down to 32-bit. So any attacker just needs to brute force this 32 bits, and then can eavesdrop on the communication. And how do we know about it? Because the standard is proprietary, it was not public, but eventually people at Midnight Blue reverse engineered it and published their results last year at Usenix. And so this is essentially one example for our motivation. There's bad crypto. So let's find it. Let's go and find a bad crypto to improve the security of all of this. Okay, so where can we find crypto? And then, I mean, of course, also then bad crypto. Well, the most simple case is just in the documents, right? So in academic papers maybe, or in standards or patents, so on and so on. But even if you don't have access to such specification documents, you might be able to reverse engineer the specification of a cipher. And that's actually what happened for Tetra, right? So the people at Midnight Blue, they use software reverse engineering. So they bought a radio, which they were sure that has to implement this TEA ciphers. And then they use some software exploits to actually get the code of the ciphers and then could write down the specification for it. But it might also be that the cipher is not implemented in software, but in hardware. So you don't have any binary, which includes the encryption algorithm, but you just have a piece of hardware where you have the implementation of cipher. And then you have to use hardware reverse engineering. And of course, the case of documents is super easy, right? Everyone can read a document, but for reverse engineering, it's a bit harder. But actually, so a subset or similar authors of the all corps are broadcasting. So the Tetra paper about Tetra 3 years ago at Usenix had a paper Where's Crypto? So by Maya Munsami and Wetzel, and Maya and Wetzel we also had the Tetra paper. They have this paper Where's Crypto, which is a reverse engineering tool. So if you have ever heard of IDA, it's a plugin for IDA. So a software reverse engineering tool, which automatically finds crypto in a binary. But for hardware, there's no such thing. And that's the gap that we, with our work, want to fill. And to do so, we introduced Hawkeye. So Hawkeye is this tool that will automatically find symmetric cryptography in hardware descriptions. But before I can tell you how Hawkeye works, we have to talk a bit about some background. So essentially about hardware reverse engineering and how symmetric cryptography is actually implemented in hardware. So first, hardware reverse engineering. There are essentially two kinds of hardwares, namely ASICs and FPGAs. So ASICs are application-specific integrated circuits, so just like microchips. And then there are also FPGAs, which are field programmable gate arrays. And there, the nice thing is that they are reconfigurable. So let's say you have a radio which implements this cryptographic algorithm. Then you don't have to produce an ASIC because that's quite expensive. You can just buy an FPGA and then use the FPGA to implement the encryption algorithm in hardware. And how does reverse engineering works then? Well, we have this chip, and the first thing is that we have to open it, right? So decapsulation, we open it, and then we have many layers in the chip. So we have to delayer the chip, and of each layer we take pictures. Yeah? And of course, it's not just your phone camera, but it's expensive hardware to actually take the images, and then those images you have to stitch together, right? Because you cannot take just one image of all of it. You have to take many small images, and then you have to process them, stitch them together, and in the end, you get something called a netlist. So a netlist is now a formal description of the hardware circuit in the ASIC, and it really is just a graph. So you have nodes and edges in the graph, right? And the graph, the nodes are then the gates in the netlist, in the circuit, and the edges are just the wires. And then once we have this formal description, we can analyze it. And for FPGAs, it's a bit easier because, like I said, they are reconfigurable. So they have this configuration, which usually is called a bit stream. And so this we can extract. Of course, I mean, you're not supposed to be able to extract it. There usually are some ways or some countermeasures that should protect the bit stream. But then there are vulnerabilities in this again, and then you are able to extract it, and then you can convert it, and again you have the netlist. So all in all, this reverse engineering process, of course, is not trivial at all, and it has been studied, and it's also like actively is studied how to do it. But for us, we abstract it away and we just work on a netlist. So we assume that we are given this netlist, and now in this netlist, we want to find symmetric cryptography. Okay, so let's talk about how symmetric cryptography is, is implemented in hardware. And there are two main approaches to do it, pipelined and round-based. So for pipelined implementation, if you, for the example, just think about something like AES, you would implement each round of the AES in hardware. For each round, you have the gates. And then in between, you have state registers. So in every clock, you compute one round. And then after 10 rounds, if it's AES 128, you have your ciphertext. And of course, this enables you to actually pipeline it, right? So it's called pipeline. So it means in every clock, you can put another plaintext in the pipeline. And then after a short initial phase, in each clock, you get one ciphertext. And on the other hand, we have the round-based approach to implement it. And there we implement the round function only once. Yeah? So it takes a lot less space or a lot less area in hardware. Yeah? So again, if you take AES, you only have to implement one round. And then, well, we have a state machine. So FSM is a finite state machine. This then controls this loop. And after 10 rounds, again, we have the ciphertext. Of course, if you're talking about symmetric cryptography, you usually also have a key schedule. But for our work, we can mostly ignore it. And then, the state register is, a register. So that's just flip-flops. So a flip-flop is a small gate which can store one bit of information, right? So, and then let's take AES again. In the state register, we just have 128 flip-flops next to each other storing the state. And then for the round function, of course, there we have gates like NANDs, NORs, inverters, XOR, and so on. But those, for the talk, we can mostly ignore it. So we just think of this as some cloud and something is in there, but we don't care too much what's in there actually. And then let's briefly talk about the data path. So how is the data flow in the implementation? And here for the pipeline, just straight, right? There's no branching out of it. It's quite obvious. And then for the round-based, well, we have this loop, and then we go to the ciphertext, and that's it, right? So quite simple. Okay, now let's briefly discuss what's special about symmetric cryptography. So what can we then actually use to find it in the netlist? And the first thing is that flip-flops in the state registers will only influence the flip-flops in the other, the flip-flops of the state register, and then in the end, the ciphertext, but nothing else. And that's quite clear, right? Because otherwise it would be somehow strange if the internal state of the cipher would influence something else in the CPU or whatnot. That would be quite insecure. So obviously that's not the case. And even more, which is quite important for us then, is that we can distinguish the flip-flops of the state register and the ciphertext. Yeah? So not going into the details there, but for example, by looking at control signals to the flip-flops, we can say, okay, those two flip-flops don't belong to the same register. And then, we are talking about symmetric cryptography, and there we have this avalanche effect, right? So if you toggle one bit in the input, you expect that roughly half of the bits in the ciphertext will change. And of course, this also means that all bits in the first state register must be connected somehow to all bits of the output, right? Because if you change something, everything is affected. Of course, only half of it. But if you change another bit, then maybe the other half is affected. Okay. And then the round function only depends on the plaintext bits and the round key bits and the inputs from the finite state machine. Again, this is quite obvious, right? It would be strange if anything else in the CPU would influence your encryption. But this is quite important for us when we then actually analyze the round function, because additional inputs are additional work, essentially. Okay, so now we can talk about our techniques, so how we actually find it, the crypto in hardware. And again, I want to remind you of the problem. We have this netlist given, so a graph, and this can be huge. So it can easily be hundreds of thousands of gates. And then we have our tool Hawkeye, and like in some very efficient way, we want that it tells us, okay, there's crypto. Yeah? So we don't want to wait a month of computation, but we want to have it quite fast. Okay, so the first step is a pre-processing step. So we are given this netlist, so some flip-flops and then some gates like inverters and NANDs, NORs, and so on. First step is to ignore everything but the flip-flops. So watch closely, we have the graph, and then we only have the flip-flops. Yeah? And then, of course, the edges we have to somehow extend. So here we have 2 edges going into this gate, and then after this, we just have 2 edges going to the flip-flop. Yeah? So that's what we call the flip-flop graph now. Yeah? We are just interested in the flip-flops. So again, I remind you, the flip-flops are what the state register is built of the flip. So every flip-flop is 1 bit in our state. And then now all of these boxes, every box is 1 flip-flop. And what we do, yeah, so this is the flip-flop graph, we just pick 1 flip-flop, just randomly. And in the end, of course, we will do it for every flip-flop. And now what we do is we propagate forward. So in this flip-flop graph, we check which other flip-flops are connected to this one and propagate forward. And now, in the example, we have 2 other flip-flops, and we just do it again, but this time for both of them. And then again, we have a set of flip-flops, and we just keep doing it. Yeah. So for every one of those, we keep propagating forward until we are left with a set or with 2 sets that are of the same size. If this happens, we will say, okay, this is a candidate for symmetric cryptography. Yeah? So then we can go back to the actual netlist and extract the actual functionality that is in between these flip-flops, and then this is the candidate for a round function. Now, I mean, this is quite simple approach, right? Which is good because it will be fast. Yeah. Again, this netlist can be huge, but this is something, yeah, propagating forward, traversing a graph, that's quite fast. And then let's briefly discuss why this will work. Again, yeah, if we start in a flip-flop which is contained in the state register, because of the avalanche effect, we are guaranteed that quite fast we will have all of the state register here. And because we can distinguish state register and ciphertext, we won't propagate out of the state register. And okay, so this tells you why it will identify a candidate for a round function if we start in the state register. And now what we also need is that we start somewhere out of crypto, so not in the state register, it will just explode. Yeah, and then so you can put a threshold and then just stop if the set gets too large. And then I tell you that we will find crypto. Okay, thank you. And then once we have this round function, once we have candidates for a round function, we analyze the round function, and okay, we can use similar techniques as we did to find the candidates for the round function to find, for example, components in the round function. So an S-box and a linear layer and so on. And then we can use known techniques to, for example, if it's SPN, to extract the S-box and then look it up in a database. Yeah? So there are some known techniques that we adapt to do this. And now, I mean, this is all heuristics, right? So better we evaluate it, and we do. But as hardware reverse engineering is actually quite a complex and costly process, this is not really an option to do it. So instead, we synthesize open source hardware descriptions ourselves. So given an implementation, we can synthesize them to have this netlist. And we did it for 3 case studies, the first being OpenTitan, which is an industry-grade chip. So it's a silicon root of trust. So essentially, it's a RISC-V processor with a lot of crypto. And actually, it's one of the few designs, open source designs, that you can find that contain crypto. So that's more or less the only thing that we could use for a big example. And then you have some smaller examples, namely cryptographic accelerators in a small system on chip. And there the idea is that we can swap out the actual crypto part. And then we have some isolated benchmarks, which are either cryptographic or, well, non-cryptographic, so that we can test or can evaluate that actually Hawkeye will find the crypto, but noise will not lead to too many false positives. And based on our results, we are quite confident that our techniques will also generalize to unknown ciphers, right? Because this is what we want to do. We want to find AES because we know that how AES works, but we want to find ciphers that we don't know yet. And our implementations are available as artifacts for crypto. Okay, for OpenTitan, which this is a schematic overview of it, there's a lot of crypto and it contains more than 400,000 of gates. But still, it takes only 44 seconds on a laptop. So in this case, Apple, so a MacBook Pro with an M2 processor, and then it finds these candidates. Yeah? So for example, the AES state and char2 and so on and so on, we get after 44 seconds. Of course, there are also some false positives. and those are mostly counters and state machines. Because if you remember what I told you, I mean, how our candidate search works, it will also find this, because they also have this locality, which we use for symmetric cryptography. But those could easily be filtered out in a post-processing step. And then for the other two case studies, so for the accelerators and the isolated benchmarks, the runtime always was in seconds, and so we observed that the runtime is roughly linear in the netlist, or in the size of the netlist. And for most of the ciphers, we actually, or Hawkeye is able to find them. And like I said, we have only a very few false positives, and most of them are counters or these state machines and could easily be filtered out. Okay, so let's end by, or I want to end by giving you some possible future work. And so when we designed Hawkeye, we more or less ignored ciphers based on shift registers. So something like Trivium, but we still evaluated Hawkeye on Trivium and Catan. And we observed that sometimes we can still find it, especially then when it's implemented in an unrolled fashion, because then it again looks a bit more like block cipher. But we believe that Hawkeye could be improved to more reliably find ciphers based on shift registers by implementing maybe another detection method for them. And also, we completely ignored side channel protected implementations. So this is something to add. And then, maybe most importantly, I mean, we don't have or had the capacities to do actual hardware reverse engineering. So we did not test on real-world devices. But if you have a device that you think might contain crypto or might be interesting to look at, then please reach out. So I'm here, and Julian, one of the co-authors, is also here, and we are happy to talk about this. So that's it. Thank you a lot.
Probably have time for maybe one very fast question if anybody's got something.
Hi, thanks for the talk. I was wondering, is there any relation between this technique of looking for this repeating pattern in flip-flops and the software analysis tools like the one on IDA?
No. So for the software analysis, it's a bit different, because you actually are talking, I mean, you can analyze on word level structures, right? We have to argue about bit level structures, but the Rares crypto paper, it essentially works by defining how the crypto should look like, and then trying to solve some graph isomorphism problems to find the crypto. So it's a bit different. Great question.
Let's thank the speaker one more time. Sorry, I'm mastering everybody's name. I'm going to talk about algebraic structure of the iterative tile. You want to catch Jack a little? Don't look right into the laser. Last one. Yeah, it's the last one. I'm wondering if the battery is low in that thing because it has trouble. Thanks for the. I don't sound this one.
Hello? Yes. So thank you for the introduction. My name is Bernd Kriepke, and this is joint work with my advisor, Goha Garelian. We are both from the University of Rostock in Germany. And I want to talk today about the algebraic structure of the iterates of chi. So of course, most of you probably know what chi is, but let's do a quick recap anyway. Chi was first introduced by Damon in his PhD thesis. And it's a function working on n-bit strings. And it's a permutation if and only if n is odd. It's a shift invariant function, which is quadratic, so all its coordinate functions have degree 2. The algebraic degree of the inverse is rather high. It's n plus 1 over 2. I don't know where the first proof of this result is in the literature, but this result has been known for some time. And then Liu, Sakar, Meyer, and Isobe found an explicit formula for the inverse of chi. And in particular, the result also shows this algebraic degree. How is chi used? So most importantly, it's used in SHA-3, but it's also used in Ascon, in Subterranean, and in raster and some variants of it. And the length always depends on the primitive. So in SHA-3 and Ascon, it's used for 5-bit length. In Subterranean, it's used for n equals 257 bits. And in raster, and agrester, there are several options for n, depending on what security level you want to have. So how does chi work? Now on, we let n be out because then it's a permutation. So chi is a function on f2 to the n, where f2, as usual, is the field with 2 elements. And it takes some input vector x and gives you an output vector y. And the entries of y are given by this formula up there. Maybe try again. No. Not true. Okay. And we see that in the formula, we use xi plus 1 and xi plus 2. And these indices are supposed to be taken modulo n. So if they go over n, then they wrap around. So, and then, of course, the natural question is, when does chi change the input? And it does so if the second term is equal to 1, which happens if both of the factors are equal to 1. So that happens if xi plus 1 is 0 and xi plus 2 is 1. So chi flips the input xi if and only if it is followed by the pattern 0, 1, which gives you a very nice intuitive definition for what chi is. And it's this can also be said by saying that chi is given by the complementing landscape star 0, 1, which is exactly this fact. So let's do a small example. Here we have 9 bits. We look at the first one, it's not followed by 0, 1, so it stays the same. Then the next one, it is followed by 0, 1, so it's flipped. Then you continue on. And then the second to last bit, it is followed by 0, 1, where we consider wraparound, so it's flipped. And then the last one followed by 1, 1, so it stays the same. What are we interested in here are the iterates of chi, namely what happens if you take some vector x and then apply chi over and over and over again. Can we predict what will happen? Can we find a closed formula for that? One reason why we are interested in that is that the inverse of chi is itself an iterate. And for the inverse, there is some formula known. So maybe there's also some formula for the iterates itself. In general, you would not expect that to be the case. Generally, iterates behave very bad. But in this case, it actually turns out to be very nice. So let's start slow. We are computing the first few iterates by hand. We're starting with some vector x. Then we're applying chi the first time. So for the first iterate, the entries are just given up there. Then for the next one, we take our first iterate and apply it, plug it again into chi, and then we get that expression. And then we can plug in the entries of the first iterate that we just obtained, get this, and then we multiply it out and simplify, etc. And then we're left with this. So it's just xi plus xi plus 4 times 1 plus xi plus 3 times 1 plus xi plus 1, which is rather surprisingly nice. So the second term in particular, the first one is xi plus some even number, and then we see it's a product of 1 plus xi plus some odd number, where the odd numbers are 1 and 3. So similarly, we can do it for the third iterate. We see that it has the same structure. So it's xi, and then we're adding some terms. And each of the terms is xi plus some even number times some terms of the form 1 plus xi plus some odd number. And this odd number always starts at 1 and ends at the even number, odd number smaller than the even number at the start. And then we can again do it for the fourth iterate. We get again a very simple formula. So it's just xi plus 8 times all these products where the odd terms are from 1 to 7. Given that all these terms appear over and over again, we give them a name. We are calling them gamma 2k. So it's just always x I plus 2k, and then all these products, 1 plus x2 I plus m, where m are all the odd numbers. And using this notation, we can summarize the results we just got in this very nice form. So chi itself is just x plus gamma 2, then chi squared is x plus gamma 4, chi cubed is x plus gamma 2 plus gamma 4 plus gamma 6, then chi 4 is x plus gamma 8. And we see there's definitely something nice going on. Now the question is, what is going on here? How can we explain it? What is the general pattern? What will continue? Before we do this, we change our notation. Because we're dealing with a lot of compositions of functions, it's not the current notation with these bits is not very well suited, because it seems a bit wrong to take some expression and plug it into xi plus 1. It seems a bit wrong. So instead, we're introducing the shift operator, which just takes some vector x, takes the first entry and puts it at the end, and the rest is shifted down. And furthermore, we're considering the Hadamard product of two vectors, or the element-wise product. So we're writing it with this O dot symbol. So vector x times O dot vector y is just all these element-wise products. And again, we can look at chi, which is given us up there. And if we, for example, look at the first entry of chi of x, the formula says, okay, it's just x1 plus x3 times 1 plus x2. And if we now look down at the vector notation, the first entry is exactly the same thing. And similar for all the other entries. So it means we can write chi just in the form identity plus the shift 2 times applied times 1 plus s, because going back, the first vector is just x itself, so the identity applied to x. Then the second vector is x but shifted 2 times. And then the last vector is x but shifted once. Okay. Yes. So, and then as we have seen before, this s2 times 1 plus s is equal to gamma 2. And then we are also using gamma 0 to denote the identity mapping, because that is a little bit more self-contained with all these gammas. And just as before, we can write gamma 2k also with this notation. So it's s to the 2k, and then all these products with all these odd terms, each with the 1 plus. So, and this notation is now a bit better, because now s actually is a function. So if we have some term, it looks very natural to plug it again into s itself compared to this bit notation down there. What's now our goal? We want to study how chi composed with itself works. We know that chi is a linear combination of all these gammas. So we're now going to study the more general problem: how do compositions of these functions gamma 2k and the linear combinations work? Of course, I'm going to skip over most of the details, but I'm going to present the key lemma basically, which says that if you take some function gamma 2m and plug into it some linear combinations of these gammas, then the result is again a linear combinations of these gammas, which is a very surprising result. In general, you would not expect that if you take some function and then the linear combinations and compose them with each other, that you again get a linear combination of these functions. I want to point out that this gamma 0 is actually very important. If that is not included in that linear combination, the result is actually false. So as an example, if you compose gamma 2 with itself, then the result is S4 times 1 plus S3, which is not, again, of some linear combinations of these gammas. Given that it's important that this gamma 0 is included, we give these functions a special name. So we'll let first G be the set of all these functions. So it's just gamma 0 plus some linear combinations of these other gammas. And then we call the maps in this set generalist chi maps. Why do we do that? Well, chi itself is in that set, and then we take that as some motivation because these functions in that set behave the same way. You will notice I'm stopping the list for these gammas at gamma n-1. Why am I doing that? It turns out that after that, all the other gammas are just the 0 map, so we don't need to include them. Now we can go to a key lemma back again and let's look at some examples. So we can, for example, compose gamma 2 with gamma 0 plus gamma 4, and then we get gamma 2 plus gamma 6. Or we can compose gamma 4 with gamma 0 plus gamma 2 plus gamma 6, and then we get gamma 4 plus gamma 6 plus gamma 10. And this looks very nice, and it looks also familiar. And how does it look familiar? Well, it looks a bit like polynomial multiplication. Let's try to make that a bit more precise. Instead of the function gamma to k, we are writing the polynomial x to the k. So instead of gamma 2, we write x to the 1. Instead of gamma 0, we write x to the 0 or 1. And instead of gamma 4, we write x to the 2. And if we multiply it out as polynomials, we get x plus x to the 3, which is the same as if we had replaced x to the 2 with x and x to gamma 2 with x and gamma 6 with x to the 3. And similar for the other example. So it looks like gamma to k behaves like the polynomial x to the k. However, there's a small exception, namely that, as I said, gamma n plus 1 is the 0 map, and all the other ones after it as well. So then x to the n plus 1 over 2 should also be the 0 polynomial. How can we achieve that? Well, we are just computing modulo this polynomial. So in this quotient ring, f to x modulo x to the n plus 1 over 2. And then using this, we get a very nice result that the composition of the functions in G behaves exactly like the polynomial multiplications for polynomials of the form 1 plus some linear combination of the power of x in this quotient ring. And this is a very strong result because it now tells us that the composition of functions in G, which we don't know a lot about, behaves exactly like polynomial multiplication in some ring, which we know a lot about. So if we find out some properties of this polynomial multiplication and these polynomials in this ring, we can then exchange also get these properties for our functions in G because they are behaving exactly the same. So here's the result just stated again. If we look at these polynomials, we notice they are all multiplicatively invertible in this ring. And in fact, their inverses are again of the same form. So the set of all these polynomials forms a group, the unit group of R. And we know, well, polynomial multiplication is commutative. And then again, because we know the composition of the functions in G behaves exactly the same way, and we know these polynomials form a group, we can also know, well, G is actually a group under composition. In particular, every function in G is a permutation. And they commute, which is not something you would expect if you did the calculations. So now we have done all this theory. What did we actually want to solve? We wanted to find the iterates of chi. We now know chi behaves exactly like the polynomial 1 plus x. And the composition of chi with itself is the same as exponentiation of 1 plus x. We saw previously this nice pattern for the first few iterates. And we can now explain it very, very easily using the first few powers of 1 plus x, as these have exactly the same form. And of course, this now generalizes. If we wanted to find what chi composed with itself 100 times is, we could just compute the 100th power of 1 plus x, and then we can just translate it. Thank you.
We have time for questions. Anybody's got a question? Anybody wants to go to dinner? I'll just ask, do you have any sense of this being useful in any cryptanalysis or anything? It's interesting. It's kind of surprising it has its properties, but do you feel like you learn anything that you can use in analyzing something like ASCON or Petrak or any of the other ciphers?
We don't know yet, but I have some ideas which might be applied, but at the same time, I'm not really an expert at this. So I might be interested in talking with someone who knows a bit more about maybe algebraic attacks, and then we can figure something out.
Also, is it efficient? Would it be efficient to using your formulas? Would it be reasonably efficient to build something that did the 100th iterative of chi? Would that be something you could do as an efficient thing in hardware? Or would it still be horrible in hardware? It's just that you could write it down mathematically.
I would expect that this would be much faster than iterating it over and over again, but I don't really know a lot about this. So.
All right, thank you. Thanks for speaking.